Hello and welcome back. Welcome to the second of our flip sessions. If you remember last time, we introduced this idea of Hooke's law and its applicability to things like springs and elastic bands and everything like that. We talked about how energy, elastic potential energy, is stored in springs and how we can calculate that. And we've also, in the lesson, we've looked at calculating the spring constant, K, and we've done some, we've had a look at, again, energy stored and work done. What we'd like to look at today is we're going to have a look at springs again, but we're going to look at some slightly more complicated setups and how Hooke's law does or perhaps doesn't apply to those. So we're going to explore that in a second, but we're also going to look at this idea of deformation. So deformation, first real introduction to our section of content on materials. So we're really looking at materials physics, material science, how materials behave under different circumstances and why they behave in the way that they do. But first, before we come on to that, I'd like you to have a think about this. So what I've got here are two springs attached to one another. Okay, so how are these springs going to behave? Well, if I quickly draw them on the board, I've got my first spring, like so, and then my second spring, and let's just redraw that. Okay, and attached to my springs is a force. Okay, I'm going to apply a force, and again we'll call it F, and we'll call this spring here spring 1, and this is spring 2. So, what I'd like to think about is how can we treat these springs in such a way that we could begin to calculate how things like their extension and their spring constant are going to relate to one another with this force F applied. Pause the video, have a go, think about how can I calculate the extension of these springs here and also the extension of the spring system. Pause the video, have a go on your sheets. Okay, so I asked you to think about this spring system as in terms of its extension. How can we calculate its extension? Well, a good starting point is to think of each of these springs as following Hooke's law individually. I mean, they still follow Hooke's law of elasticity. Nothing's changed about that. Just because they're attached to one another doesn't mean that that stops holding true. So we can say for this first spring that F is going to be equal to Kx, and again for the second spring that F is going to be equal to Kx. But what I really wanted you to think about was the extension of this spring system. So what we can also say, quite handily, is that the total extension, X total, so the extension of both spring 1 and 2 combined as a system is going to be equal to extension of spring 1 plus the extension of spring 2. Or, in the case of this example, both these springs are identical, so we can say that X total is going to be equal to 2x. Now this, x total is equal to 2x, is based on one pretty big assumption. So what I'd like to do is now pause the video again and have a think. What assumptions have I made in writing that formula? Pause the video and write that on your sheets. Okay, so you've hopefully recognised that the major assumption that I've made here is that the spring constants of both these springs are the same. Their K value are the same, so K1 and K2 are equal. Okay, so make sure you've added that on, so assuming K1 is equal to K2. So assuming that both springs are identical, and of course the forces are going to be the same as well, because you've got this same force being transferred throughout both springs evenly. So both springs are undergoing the same force, and this relationship holds true if their spring constants are the same. So what we can say is that the spring constant K for a pair or for a number of springs in series is going to be equal to the force applied divided by the total extension, or F is equal to 2x. Okay, so what I'd like you to think about now is how could we potentially work out this K K series value, this spring constant value for a pair or more of springs in series, if we didn't know what F is, pause the video, have a go. If you can't quite work it out, watch on a little bit further and then pause it again and see how far you get with it on your sheets. Have a go at that now. Okay, so a quick hint depending on how far you got with that. If you haven't quite got that, think about this. K series is equal to F over 2x. Now, remember Hooke's law, which is F equals Kx. See if you can use that now and have a go. If you still can't if you still can't work it out, watch on a little bit more and see if you get the idea. If you have got it, keep on watching and we'll go through it. Okay, hopefully you've got that, and hopefully you've recognised that we can just do a quick substitution of this F, this force here, with Kx. So we can say that K for series is equal to K over x divided by 2x, which is, those x's are going to cancel, so we end up with K over 2, which is equal to K of the series. So, for two springs that are identical, we can say that the spring stiffness constant for the system is equal to a half of the K value for just one spring. Have a think about that. Just take a moment, pause the video, and think about what the implications for that are. Just think about that in your head. You don't have to write anything down. Okay, and see if you just make sure you've got all that straight in your head. That the spring constant for a pair of springs in series is equal to a half of the spring constant of just one of those springs, assuming they are identical. And that might be a little bit counterintuitive. You might have expected for the spring stiffness constant not to have changed. I mean, at the end of the day, both these springs are the same. Nothing's really changed. The springs just got longer. But actually, hopefully with this explanation, I've proven to you and shown to you that actually they do change. So, if you don't quite follow that, re-watch part of it, watch it all the way through again, and hopefully you'll pick it up. Otherwise, we will go through it again in the lesson. But hopefully you've got that. Okay, so hopefully you're now all okay with the idea of springs in series. So let's think about the opposite of series. Let's think about parallel. If I've got two springs in parallel, what happens then? So again, we'll talk about it in the same way. We'll go through it in the same process. Let's start off by drawing them. So I've got two springs in parallel. Okay, like so, and again we've got a force F applied down the bottom there. Okay, so what I'd like you to think about now is if F equals Kx for spring 1 and F equals Kx for spring 2, what is the force going to be? What is the tensional force going to be on each of these springs? Pause the video, have a quick go at that on your sheet. Okay, hopefully what you've got written down is that the force on each spring is going to be half of this total. So F1 is going to be equal to F over 2, and again, likewise, F2 is going to be equal to F over 2 again. Okay, so basically what we can say is for each spring, the tensional force that is imparted on each is exactly half. Again, assuming that our spring constant is the same. Now, what I'd like you to do is pause the video, and can you think about what the extension might be? Can you come up with a formula, using this information that I've got on the board, can you come up with a formula for extension based on those assumptions that I've already talked about? The spring constant being exactly the same. Pause the video and have a go. If you don't know where to start, you're a bit stuck, stop, have a think about what we've done for series, rewatch that, and if you're still stuck, watch on a little bit further and I'll give you a bit of a hint. Okay, hopefully you've got that, or you've made an attempt, or at least you've watched back and seen what we did for series. If you haven't quite got it yet, just take this as a hint. Hooke's law says that extension is equal to F over K. Okay, if you haven't quite got that, pause the video again, stop, have a think about this relationship, okay, and how you might be able to use that to create how you might be able to use that and the information that's already on the board to create a new formula for extension of the spring system. Pause the video, have a go at that. Okay, hopefully you've got something now. So hopefully you've recalled that X is equal to F over K, our spring stiffness constant. And we can see here that the force applied to each spring is actually the total force divided by 2. So we can say that X is equal to F over 2, again divided by K, which is the same as saying F over 2. K is equal to our extension. Now hopefully that's what you've got, and hopefully you've already written that down, because what this is basically saying, this bit here, okay, which is quite important, so again make sure you get that written down, but what this says is that for whatever force we apply, we're going to get half the extension we would otherwise have got if we'd had just a single spring, which is very interesting, very helpful. But what I'd like you to do now is, can you, just like we did before with series, can you work out a spring stiffness constant for this system of springs in parallel? So we want one stiffness constant that summarises this entire system. Pause the video, have a think about it, and have a quick go. If you don't quite get it, watch on, there's a little hint to follow. Okay, so let's go through this. Let's just give you a quick hint if you haven't quite got there. So what I asked you to do was find Kp, the spring stiffness constant for our parallel spring system, in terms of K, okay, again with our big assumption that, assuming that all springs are identical. Okay, so hopefully what you've remembered and what you've already written is that Kp is equal to F, our force, divided by our extension. Okay, our spring system follows Hooke's law. It obeys Hooke's law of elasticity. Okay, it will still produce a straight line graph, so we can immediately write that down as something we already know. We can also say that we know that extension is equal to force divided by 2K, our spring stiffness constant of our original springs, our original springs individually. Now, if you haven't quite got an answer, okay, pause the video again, have a look at these two bits of information and see if you can come up with a way of expressing K little p, okay, the spring stiffness constant of our parallel spring system, in terms of just K, okay, the stiffness constant for one spring, or for the individual spring. Pause the video, have a go at that. Okay, so what you've hopefully recognised is that we can substitute this x here for this x over here. So all I'm going to do is replace this x with this f divided by 2k term, so I can say that kp is equal to f divided by f, another f, over 2k. And if I simplify that down further, that becomes 2k by itself, because the f's just cancel. So we can say that 2k is equal to k of the, so we can say that, sorry, let me start again. We can say that 2k is equal to the spring stiffness constant of our system of parallel springs. Hopefully you've got that down. If you haven't got that down, get it into your notes now, write it on your sheet. And if you haven't quite followed that explanation of how that works, okay, just re-watch the video, okay, and see if you can follow it. Okay, hopefully you've got all of that down, all that information that we talked about, and you filled out your sheet. Don't worry if you don't quite see how these concepts quite marry up in the real world. Don't worry about that. We're going to do some practical work in the lesson looking at these things and how they actually work and what this actually means in real life. So don't worry about that. Make sure you've got it all down though, because it is important and it is useful to have. Right, what I'd like to do now is move on to our first look at our materials section. So, one of the key things you need to know for the lesson is this idea of elastic deformation. Now, elastic deformation is exactly what we see when we have a rubber band, or even something like a tyre. This is just a bike tyre. Again, I've got an inner tube. Okay, I can stretch it. Likewise with the tyre, I can stretch it. All elastic deformation is what happens when it returns to its original shape. Okay, a force is applied, a tensional force is applied to something. Okay, it might be my elastic band, it might be the steel in a spring. Okay, I apply a tensional force, and when I remove that force, okay, it returns to its original shape. So, having me just told you a definition, what I'd like you to do is write your own definition for elastic deformation without pausing and rewinding and writing down exactly what I've just said. So, hopefully you've got that. Hopefully you've got the concept at least. Can you now write your own definition for elastic deformation? Pause the video, have a go. Okay, great. Hopefully you've all now got your own definition down, written down on your sheet for elastic deformation. What I'd like to do now is we're going to talk about the other type of deformation, which is plastic deformation. So for this bit, you will need your carrier bag. Now, plastic deformation is when a small force is applied and the material doesn't fracture, but when that force is removed, it doesn't return to its original shape. So, for instance, a really common example is blue tack. I've applied a force to it, I've now removed that force, but it hasn't returned to its original shape. So you can see that really clearly with clay or blue tack or anything like that. Okay, I just apply a force, it changes the shape, and when I remove the force, it doesn't return back to its original one. Another really clear example plastic deformation is, funnily enough, with a plastic carrier bag. Okay, what you can do, okay, is if you apply a small force, what you'll see, I don't know if you can see it on the camera, is that my plastic bag has actually changed colour. It's changed shape. It's only changed colour where it's changed shape. So have a go with yours. Apply a small force to your plastic bag and see what happens. Watch it change colour. Watch it change shape. It works best with a coloured bag, but if you've only got a white one to hand, you can see it as well, but you have to look a little bit closer. That's what plastic deformation is. So what I'd like you to do is, can you get written again onto your sheet a definition for plastic deformation? Okay, hopefully you've got that down. Okay, so I've given you a couple of examples: blue tack, modelling clay, carrier bag, all examples of materials that undergo this plastic deformation process. But interestingly, so things like ice, okay, if the force is applied for long enough, ice will plastically deform. Okay, think about a glacier moving over long periods of time, admittedly, but that again is an example of plastic deformation. It doesn't return back to its shape after that force has been removed. So there you go, there's a nice real world example to end on what we're going to talk about in the next lesson. So in the lesson we will be talking about springs in series and parallel. We're going to do some practical work associated with that, and we'll also be looking at this idea of plastic and elastic deformation as well. So what I need you to do, make sure you bring your sheets to the lesson and make sure that you have responded to this flip in terms of how you found it, whether you found it useful or otherwise. Thank you very much, and I will see you in the lesson.